it's important to understand that all these performance metrics I've been talking about are going to be overly optimistic if you fit the model and test the model on the exact same observations. We call this resubstitution statistics. Fitting and evaluating the model on the same subjects can lead to overfitting. As I mentioned before, overfitting is when you fit your model to the quirks of your particular sample, to the noise really, allowing you to get seemingly great model fit, but basically no predictive ability when the model is applied to a new sample. I showed you these graphs before. Here we have an underfit model. So if I just put a straight line fit to these points, my root mean squared error is pretty high. I can do better in the root mean squared error, get better fit closer to the points if I make a nice curve there. However, I can do really great, or it's going to look really great. My root mean squared error is going to look incredibly small if I put a whole bunch of parameters in the model and basically fit individual points in that data. So my model is going to look great if I just look at the model performance metric of root mean squared error. It's going to look really, really small, and I'm going to think I did a great job in fitting that data. But that's actually overfit. And the way that you can show it's overfit is to try to apply that model to a new data set, a new sample from the same population. So when I did that here, these blue dots actually represent an entirely new sample randomly drawn from the same population that I used to draw those red dots. And when I apply my overfit model here on the left, that's the model in red, you can see that I do really badly. I'm quite far, in many cases, from the line. My root mean squared error has now blown up. It's huge. In other words, my model does very poorly. It has a terrible fit on my new data. However, when I take the same model, that nice curved model that I fit before, and I try to see how far are my new data points from that line, how good is the fit there, I actually get pretty good root mean squared error. It might get slightly worse than before, but it pretty much stays at a decent level because I have a good fit model. So we want to avoid the overfitting that you see on the left. How do you know if the model is overfit? So you get these measures of model performance out and they look great. How do you know if your model is overfit? And the key is that we have to do validation. When you're doing a predictive model, it's extremely important that you do some kind of validation. So validation can be either external or internal. External is the cleanest. You take your model, like I just did in the example I just showed you, and you apply it to a totally new sample. And then you measure your predictive ability, that is your goodness of fit or your discrimination or your calibration, on how well does this model apply to this completely new sample. That's the best. It's going to tell you the most about how good your model generalizes to all populations. But we can't always do that because, of course, that means you've got to go out and do another study. So a lot of times we compromise and we do what's called internal validation. In internal validation, we're going to measure our predictive ability on held out data from the original sample. I'll say what that means in just a minute. Basically, the idea is you want to hold out some part of your data at any given time and make sure that you are not fitting your model and testing your model on the same data. There's lots of ways to do that. I've already shown you external validation. We just saw that. When I had that overfit model, it fit great on the training data on the left here, but when I applied it to that new data, the test data, it fit terribly. So that tells us, doing that validation tells us it was an overfit model and it's actually not a good predictive model. And again, when we had a nicely fit, a well-fit model, it does very well on the test data. But it's hard to go out and gather an entirely new data set. That's the ideal, but it's not always possible for a given study. A compromise is to do internal validation. Here, you're going to hold out some of the data when fitting your model, and then you test the data only on the observations that were held out of the fitting. And there's a number of ways to do this: split sample, cross-validation, and bootstrap validation. I want to point out one thing that tends to confuse people is when you do cross-validation and bootstrap validation, you end up fitting more than one model. And people get confused about what model am I actually reporting in my paper. Keep in mind that your initial model, the very first one you fit, is the model that you're going to report. The purpose of the validation is not to create a new model, but to calculate a correct metric of model performance for that initial model. So if you calculate the C statistic using the same data that you use to fit the model, so you take the data, you fit the model, and then you test the model on that same exact data, maybe your C statistic comes out to be 80%, but that's too rosy a picture. If you then do some kind of cross-validation, you would get a more accurate estimate of the discriminative ability of your model, and maybe the C statistic then comes out to be 70%. So you're going to report your original model, but the C statistic of 70% rather than 80%. Another thing to note about internal validation is it's not as good as external validation. As I've mentioned, external validation can tell you something about how generalizable your model is to other populations, whereas internal validation cannot. Split sample validation is easy to do. You're just going to take all your data, you split the original data into a training set and a test set. You take the training set, you fit the model, and then you take the model and you test it on the test set. Easy to do, but it requires a lot of data because you have to hold a bunch of your data out, so you kind of lose some of your sample size. So if you have a big data set, great, you can do it that way, but you pay a cost in terms of reducing your sample size for the training. Cross-validation and Bootstrap validation get around this. The advantage is you get to use all of your data by being a little bit clever. So you could do something called leave one out cross-validation, for example. So in leave one out cross-validation, you fit your model, but you fit it on all the observations except one. You hold out one observation at a time. So you fit a whole model, and then you take that one observation and you calculate the predicted value for that person you held out. You calculate that using your newly fitted model. And then you compare it to their actual value. So you get a residual for the one person that was held out in the fitting of that model. And then you repeat this. So you're going to fit a new model. You're going to hold out a different person. You're going to calculate their residual. And you're going to do this over and over and over again. And then you can average all of those residuals. And it will be a clean estimate of the residual because it will be all from models where the person being tested was not used in the fitting of the model. That's one approach. Another approach that I'm going to talk about in more detail in an upcoming module is 10-fold cross-validation. Here you're going to do something similar, except you fit the model on 9/10 of the data while holding out the remaining 10th, test the model on that held out 10th, and then you repeat that 10 times, and again you average the predictive performance across all these models. Very similar to leave one out cross-validation, but you only have 10 folds here. Bootstrap validation I'm also going to talk about in an upcoming module, but the idea here is you're going to fit the model on Bootstrap samples of your data. So you're going to take a Bootstrap sample, which I talked about earlier. You're going to fit the model on that data. Some of the data have been held out. In fact, in any Bootstrap sample, about a third of the observations are going to be left out. So you can then test the model either on the original sample or on the out-of-bag observations, the observations that were left out of your model fitting. And again, summarize predictive performance across these models. I'll go into more detail now about 10-fold and Bootstrap validation in these upcoming modules.